and share my screen. Can you all see my screen okay?
Yeah.
Okay. So thank you both for joining me in this session discussing quantum computing. Some of these may be familiar to folks who saw my attempt at the lecture last week, but we're just going to run through them anyway, just so that we have a full and complete recording. So with that, let's get started. On session 2, what is quantum computing? So I have a question for the audience. Why do people want to build a quantum computer?
To increase speed in operations.
Yeah. So basically, all the conversation around quantum computing is people thinking that a quantum computer, a quantum chip, a QPU, if you will be faster at performing certain calculations. And I bring this up first because I think one of the most common misconceptions people think is that quantum computers are just generally better at everything. And that's not true. Quantum computers are only faster at a few kind of select problems, and we don't even fully understand in full generality if quantum computers are better than classical. But we have some examples of algorithms where quantum computers happen to be faster, and so a good thing to have in our mind when we think of quantum computers, in the same way that if you play games on your PC will handle most of its day-to-day operations using its CPU, the central processing unit, the chip. But if you're playing a video game and you want to render those graphics, you want a specialized computer chip called a GPU, graphics processing unit, which is specially designed to be better than a CPU at specifically that type of task. So a QPU, in our minds, we should think, is another type of specialized chip. So let's look at an example of the first real-world application of a quantum computer that can do a task faster. Can somebody tell me what it means to factor a number? So I've got an example here up on the screen, 12 being factored. If I were to give you a different number, what does it mean to factor a number?
To break it into its smallest pieces.
Exactly. And those smallest pieces are referred to as prime numbers. So here, the prime factors of 12 are 2 and 2 and 3. And we, as you say, they're the smallest pieces. You could think of them almost as the atoms of the integers. We say they're the smallest pieces because you can't take 2 and factor it into anything else. It only factors as 2 and 1. So there's no smaller number that you can go to. So factoring the number 12 isn't a particularly exciting problem. You could do that pretty easily with pen and paper. Classical computers are very good at that. But if you want to factor this number, which is an RSA 2048-bit encryption key, what this number does is it enables the secure transfer of information online. And the way that it accomplishes this is by encrypting information. And the only way to decrypt the information is if you know the prime factors of this very long number. And classical computers take very long to do this. It's estimated that a supercomputer, some of the biggest computers we have ever built, would take 300 trillion years, which, putting that into perspective, relative to the age of the universe, 13 to 14 billion, that is ungodly amounts of time, more than the universe has even existed for a classical computer, just to break this, factor this long number. By contrast, a quantum computer is estimated that if you could build a quantum computer that was large enough, you could factor this number in about 10 seconds. And anybody who potentially was in the first attempt of this lecture last week, can you tell me what the quantum algorithm is called that factors numbers? Think waves on a shore. Shore's algorithm is the name for this. And I bring this up, I show you this diagram. This diagram shows you how you could implement this algorithm, what steps you would need to perform and in what order on a quantum computer. But what the bottom line is, this is probably the most famous quantum algorithm in the field. So just the takeaway from this is Shor's algorithm gives you this enormous exponential speed up in factoring numbers, taking a calculation that would require 300 trillion years, possibly, to something that could be done in 10 seconds. If we can build a computer big enough to use Shor's algorithm, we would be in trouble, because that would render the information security that we rely on the internet to use all of the digital infrastructure that we use today, all of that would be vulnerable to a Shor attack using Shor's algorithm. And so we'll talk a little bit about the requirements, the fact that we can't yet use Shor's algorithm. And that actually might be a good thing. Let me pause there. What are people's thoughts or reactions here? Any questions?
I just described speed with which we can calculate how fast we can find the answer.
Yep, exactly. And so Shor's algorithm is an example of an application of a quantum computer that gives you this exponential speed up. Yeah, exactly. And I want to contrast this. Remember I said quantum computers are not good at everything. They're not faster at every application. And in fact, if you wanted to build a quantum computer and tell it to add 1 + 1 = 2, it would be embarrassingly difficult to do such a simple, even that simple calculation on a quantum computer. So just keep this in mind, this idea that quantum computers are blazingly fast at some things, not so fast at others. You would never want to use a quantum computer to do basic addition. Classical computers are certainly the best for arithmetic and such applications which we rely on. Okay, moving on from here. Any final questions on this section? Okay. So I want to contrast quantum versus classical computing. We've established that there's a difference. We've established that quantum and classical computers are good or bad at different tasks. And the basic fundamental difference that you'll hear about if you ever pick up a popular article on quantum computing is that quantum relies on a different fundamental unit of information. In classical computing, we have bits or binary. Everything your computer does is in the language of ones and zeros. Stream a video, send a text message, take a photo. All of that is facilitated on a digital device by storing and sending and processing that information as long strings of ones and zeros. Quantum computers are fundamentally different. Rather than a bit, they rely on qubits. And a qubit is an example of a type of information which is not binary. It's able to not just exist in states like 0 or 1, as you can see on the right-hand side of the screen, but you can imagine being able to exist in any state on this globe where the north and south poles are 0 and 1, but you have access to all of these additional states that are not expressible as simple binary. And this extra expressibility is part of what we think is the reason for the power of quantum computers. And folks who've seen some of my lectures from the hackathon will be somewhat familiar with this. But these qubits are able to engage not just in the transitions between 0 and 1, the flipping of bits that characterizes most of classical computing, but they're also able to engage in uniquely quantum processes and to leverage those for computation. And so the piece that most people will hear about as kind of the secret sauce that makes quantum computers, we believe, makes quantum computers fast at certain tasks is entanglement. But entanglement, superposition, and phase rotation, all three of these are required for full quantum computation. And these are a phenomenon which we've discussed, in the previous lecture in session 1, as not really having much of a classical analog. These are unique phenomena. And it's exciting, I got into this field because I was excited to see how such unique quantum phenomenon could be leveraged for building fast computer programs. And that's still a very active area of research. We don't fully understand, even the most noteworthy experts in our field, specifically Peter Shor, we don't understand how, in general, how these quantum phenomena lead to faster programs. It's a very active area of research. I'm going to pause there. Do folks have questions on, the basic idea is just quantum is different from classical because you have access to qubits rather than simple binary. And qubits are different from bits because they have access to this whole new suite of quantum computational gates, quantum computational phenomena. Do people have questions on this? I'll pause here.
No, not
Yeah,
at the
good.
moment.
Okay. So then, why would we want to, why are we doing all this? We're building quantum computers to produce faster calculations. And many of the most promising, in my view at least, many of the most promising applications are in chemistry and material science. So we have all of these chemical reactions that, we can study in a chemistry context. In a laboratory, you can mix chemicals into a beaker, see what happens. But if you want to streamline the discovery of new chemical compounds, new medicines, or new materials, trying to predict the outcome of a reaction that you have never tried, this is a problem which we believe is specifically suited to quantum computers. And the reason is that whether it's drug discovery or material science, the basic behavior of these molecules in these reactions is quantum mechanical. Right now, we have for many decades tried to build algorithms on classical computers to predict the behavior of these quantum reactions. And the hope is that if your computer is quantum, perhaps it will have an easier time predicting the outcomes of these experiments that might help you decide how to put together these materials. Think how could you build a material that is more efficient at taking in solar energy on a solar panel? Or how could you build a pharmaceutical drug which is able to treat a particular ailment but has fewer side effects? Being able to predict the outcomes of those experiments can help fast track the process of discovery and hopefully give us access to novel materials and drugs that we currently are unable to find in the vast space of every possible combination. We hope that quantum computers will be suited for this. And in fact, the inventor of the person who came up with the idea of quantum computing, which is a very famous quantum physicist by the name of Richard Feynman. Feynman, this was his original idea of what a quantum computer would be useful for back in the 80s. And he said, if you're trying to simulate nature and nature isn't classical, it's quantum, then you should make sure that your simulation is coming from a quantum device, a quantum computer. And so that original kind of pitch, that idea that Feynman came up with in the 80s is in many reasons why this entire industry now exists. Because people kind of looked into this, they found Shor's algorithm, they found other algorithms specifically for chemistry and simulation. And that's kind of where we're at today. I think I'm gonna pause there for questions. Just the kind of motivation for why we want to build these devices in the first place. Anybody have thoughts they want to ask or comments to share? I'm not hearing
That's
much.
just me.
Oh, what was that,
No,
Pavel?
I was just trying to say that, I mean, if we see nature in the quantum field, but what if we see nature in other field we shouldn't know yet, we haven't discovered? So it probably means that we have to find another computer then later on.
Right. So you're talking about, like, maybe there's other areas where quantum computers will be useful for.
Well, in that sense as well, yes.
Well, that's almost a perfect comment to lead me into the very next slide, because it's not just simulation or chemistry that quantum computers have been found might lead to some advantage. There's a large number of these. Machine learning and AI is a big one. That was my area of research as a graduate student. Cyber terrorism, that's Shor's algorithm. That's what we talked about a moment ago. If you can break RSA encryption by factoring that big number, that spells trouble. We've got drug discovery we talked about, but there's also other applications. People are hopeful that quantum computers will be useful in finance, logistics, chemistry, and materials, and others. But these are the primary components that you'll hear talked about most frequently. And just to kind of emphasize, none of these work yet. None of these have delivered an advantage that a classical computer cannot already find. So we're still very much, as a field in quantum computing, we're in the exploratory phase where we haven't yet been able to build a large enough quantum computer that is powerful enough to really yield unique advantages in these areas. And that kind of leads me into the next portion, which is kind of the mission of quantum computing as it stands today. Essentially, the primary challenge is how to build a quantum computer that is large enough and well enough controlled that you can use it with enough power to solve some of these big, difficult problems in chemistry or in other fields. So we've talked about the smallest unit of the quantum computer is the qubit, but your computer, might have a terabyte on its hard drive. That's a lot of bits. So the idea is you need a lot more qubits if you're going to build a quantum computer that is able to do anything interesting. And a lot of people, a lot of different companies have a lot of different ideas about how you could build a quantum computer, what your qubits are made out of. Folks like Quantinuum and IonQ are building their qubits out of individual ions. So those are charged atoms. And the picture that you're seeing, if you see these kind of two ballpoint pen looking devices, those are optical tweezers. At the very center of the photo, you'll see a little tiny speck. And that speck, this is actually a famous photograph, that speck is one atom. People took a picture of an actual atom that we had held in this optical tweezer. And Quantinuum and IonQ are trying to use that fundamental technology to build a quantum computer where each atom is a qubit. Others, like Rigetti, Google, and IBM, are leveraging what are called superconducting circuits. I'm not going to dig in too much to what those are, but it is just another popular medium for developing a quantum computer. The fundamental qubits are these little rings of current. We can talk about that more, but it kind of gets us a little farther into the technical weeds than I would like to go. So I'll leave superconducting at that. Just keep in mind, superconducting is the area of Google and IBM, which are two of the biggest companies involved in quantum computing right now. We've also got people who are building quantum computers where the qubits are made out of individual particles of light. So photonic quantum computing, quantum computers whose qubits are made of photons, which are the individual quanta of light. And then finally, very similar to actually what IonQ and Quantinuum are doing, but companies like Quera and others are building their qubits out of non-charged atoms. So these are just atoms rather than ions. We can talk a little bit about the difference, but they're essentially a very similar idea. Atoms trapped in optical tweezers that you can kind of hopefully scale up to build a quantum computer with many, many qubits, where each qubit is a trapped atom. So whether it's atoms or ions or superconducting circuits or photons, there is even more ways people are trying to build their qubits. But these are the four, in my mind, the primary methods. And we're going to see a fun video, get to take a look at some of the work Quera is doing on how finally they can control these individual atoms. It's very exciting. Like, just to think about this for a minute, we are trying to build technology that is made out of the smallest pieces of matter, some of the smallest pieces of matter we can find. Controlling individual atoms is fantastically challenging. And as a result, you can imagine it's tricky to control a lot of these at once. And that kind of leads us into, I want to just kind of give you a sense of, we talked about the big mission of quantum computing is to build a big enough computer. Well, what is standing in our way? All of these technologies that I've just mentioned share a very similar challenge, which is kind of universal across methods, which is that quantum bits, if you're trying to build a computer with an individual atom, that's very difficult. And in fact, qubits are very fragile objects. They require really carefully controlled conditions to exist in a quantum state at all. Has anybody seen a picture of this kind of golden chandelier looking thing? Does anybody tell me what this golden thing is?
Either gold or copper.
Say again.
It's either gold or it's copper.
For sure. My question is like, what does this device do?
It stimulates the universe.
What was that, Abby? You're breaking up a little bit.
It stimulates the coldest temperature that's possible.
Yeah, I think I caught that. You said it creates the coldest temperatures, some of the coldest places in the universe. It's true. In fact, if you go on Google and you Google quantum computer and you look at images, you're going to see a picture of one of these. But the reality is that if you look at the picture on the right, the quantum computer is only the little tiny piece at the very bottom of the right-hand picture. This entire apparatus, 99% of it is not actually a quantum computer. It's a refrigerator. It's what's called a dilution fridge. And the dilution fridge, you see how it has these horizontal sections. Each of the horizontal sections is cooled another order of magnitude, another extreme level of cold down. So the point at the very bottom of it is the coldest part of the dilution fridge. And as Abby pointed out, the vacuum of space is something like 2.7 Kelvin, very cold. This thing is orders of magnitude colder than the vacuum of space. It's a remarkable feat of engineering just to make the dilution fridge. And again, the purpose of this refrigerator is so that your qubits can even have a hope at existing and being computed with. In general, a good way to think about a way to create a quantum experiment, a way to create a set of qubits, is that you have to produce an experiment which is extremely cold. So that's why we just took a look at the dilution fridge, and extremely quiet or isolated from any kind of sources of noise that might be in the environment. That's how you make stable qubits. Qubits can't be stable if there's a lot of heat. The heat means that the particles around it are jiggling or moving at a higher velocity. They're jostling it around, like if you're in a very busy on a very busy sidewalk. It's very hard to maintain a coherent thread of thought, which is maybe a nice analogy. Similarly, if you're in a room where everybody's talking over each other and it's very loud and hard to hear, it's similarly hard to get any messages across or to think. And so calming down these sources of noise, cooling down to a very cold experiment, and then isolating your qubits from any sources of noise outside of the experiment is critical for building a single successful qubit. And that's actually not too hard to do. In the big project of quantum technology, it's easy to make a single atom or a single superconducting loop or a single photonic circuit. It's easy to build a single qubit that isn't connected to anything and is very cold. It's very cold, very quiet. And you can have a very nice, stable quantum bit if you do it that way. But here's the challenge. We have something what's called the connectivity trade-off, which is that if you have an atom which is perfectly isolated from its environment, that means it's isolated from you, the programmer. And as the programmer, you need to be able to talk to each of your qubits to tell them how to change, to send computational gates to them, to transform their state. So think of, you have this qubit, you're going to try and build a quantum computer, which has lots of these qubits. I've only got 9 here, but think, we're in the regime now where some of the biggest experiments that are being built are in the order of 1,000 qubits. And for sure, we would need something like millions or possibly billions. So lots of these qubits. And each qubit has to be connected to you, the programmer. So right away, that connection, that black line that connects the qubit to the programmer, that is reducing the quiet that we said we needed for the bit to be stable. Because it can hear you, it's not isolated from the programmer. It's already going to have a little bit of a challenge, but still a single qubit that you can connect to that you can talk to as the programmer. That's not too hard to make. What becomes difficult to make is when you put a bunch of qubits in here. And we talked about in the last lecture about how people believe that entanglement is one of the critical resources for quantum computing. And you can think of entanglement, we won't get into it too much today. Think of it just if you're building a quantum chip and you want it to be able to entangle maybe the center qubit with one of the other qubits, those qubits have to be able to talk to each other. So again, each connection is reducing that quiet. You can have them all very cold. That's something you can do with your dilution fridge. But every connection you makes the qubit susceptible to hearing the chatter from its neighbors. And so imagine each qubit is connected to you. They all have to be minimally connected to each other if this is going to work as a chip. And so all of those connections that you see on the screen are contributing to the biggest challenge facing quantum today, which is noise. It's referred to as noise, and we won't get into the technical details of what exactly noise is, but I hope I've given you kind of a qualitative sense of noise being interference from the environment, interference from your neighbors that you need if you're going to build a big enough experiment that can entangle with enough components, but that presents challenges because those connections also introduce noise into your system. I'm going to pause there. Do folks have thoughts or questions about this? Kind of the connectivity trade-off I'm trying to discuss is as you add more qubits and as you connect those qubits together, you are adding more noise into your system that makes it harder for your calculations to perform correctly. Questions about this?
Not at the moment.
All right. So yeah, and what I wanted to show you is this is an actual picture of a quantum chip that has 5 qubits. And this is maybe a little diagram that connects to the graph that we were just looking at. I've labeled the qubits according to the picture. You can see these blue squiggles are around the border. They're labeled as resonators. Those are the connection that each qubit has with you, the programmer. Those blue resonators are how the programmer can control each of the individual qubits. And then the green and the yellow resonators are facilitating the connections between qubits into this, this star geometry. This is a very old chip. I say very old. It's maybe 5 years old, which is ancient in the time scale of quantum computing. But this is what a superconducting quantum chip looks like. People will put this chip at the bottom of that dilution refrigerator that we saw, and wiring it up in this way is a nice early experiment to just test out, can we have a 5-bit computer? Again, remembering we need hundreds, thousands, maybe millions or billions of these, but this is a first start. And this chip is very old news. Today we have chips that are, full, some companies like IonQ, they boast full connectivity between all their qubits. They've got, hundreds of these qubits wired all together. But again, that connectivity trade-off means that as you pack more chips together and as you connect them all to each other, you're going to have big issues with noise. And again, that's where quantum computing is faltering right now. We are struggling to perform computations because when we build a big enough experiment to be useful, that experiment suddenly has a big issue with noise in the circuit. And a lot of people have a lot of ideas about how to get around it, but it's not a problem that we've solved yet. And I wanted to just circle back on this kind of phenomenal level of control at the heart of all this engineering, which is we are controlling individual atoms. We're photographing individual atoms, and then we're building them into these large arrays. And I want to show you this little animation from the company Quera, which builds these trapped atom experiments in optical tweezers. Video, I don't think it comes with sound, but each dot is an actual atom. And what they are able to do is to dynamically control all of these atoms to move them around. And as you see them move close to a neighbor, those are the interactions, the line between two atoms. So this like flexible way of doing things is kind of at the cutting edge right now of what people are thinking in terms of building these experiments. And it blows my mind. I mean, we're building hundreds or thousands of atoms that we're individually controlling and interacting with each other. I just think there's nothing cooler. But I'll pause there. Folks have questions on that animation at all? We're going to move on to the next section.
No, we're good.
Okay. So we're going to talk a little bit about what these machines do. We've talked about the challenges of building them. We've talked in the big picture about they're good at some tasks and not others. And some of this is going to feel very familiar to folks who are part of the hackathon. In classical computing, we kind of base our entire premise of computation around the transistor, which is that component on the left. And we can, that's a large example of a transistor that you might use in a school project. But if you pick up your phone, that thing has, a billion transistors on a single chip inside of it. It's one of the most sophisticated industrial processes we've ever made, shrinking these transistors down. And that shrinking of transistors and packing more and more of them on a chip is what makes our computers faster every year. So there's this nice game. Many of you have tried the NAND game, where you can learn how a simple transistor circuit, which is just a current flip, so it can choose whether or not current passes or not. We talked last time about how that utilizes superconducting materials. We're not going to get into that too much, but the simple ability to allow current to pass or not, a bit to change from a 1 to a 0, gives you the ability to build algorithms of any kind with a classical computer. That's all you really need to kind of build bigger and more sophisticated programs, from social media to video games. Everything is basically flipping bits using these transistors. Those transistors give rise to these kind of fundamental logic gates and these computational circuits that we've talked about in the past. But I want to focus primarily on the quantum side, where we've talked about how you have the north and the south poles of your qubit correspond to a 1 or a 0. So you still have the ability to do these bit flips and kind of house this classical computational framework inside of quantum. But you also have these extra gates, these entanglement gates, superposition gates. So in this diagram on the right, H is the superposition gate, the Hadamard gate. T is the phase rotation. It's one of the smaller increments of phase rotation. And then the kind of two-body gate that you see, the circle plus with the control, that's the control not gate. Or if you're familiar with classical computation, that's the XOR gate. And the project of building quantum programs for any of the applications that we've talked about is figuring out what order to put these fundamental operations to produce a calculation that is faster than classical. And like I said, this is still an ongoing area of research that we don't have good general understanding of how these quantum phenomena yield speed up. But it is believed that particularly entanglement is a critical resource for that. That's all I'm going to say on that. There's a lot more in quantum algorithms that we could discuss. But for today, I want to give a little spotlight on this drug discovery application that I mentioned, and give kind of a little bit more concrete idea of what I mean when I say we want to speed this up. So the process of drug discovery, as it exists right now for the modern pharmaceutical industry, is a very long process. The discovery and preclinical research portion takes 4 to 7 years, just figuring out what drugs you might want to try in human trials. And then human trials and data review could take another decade. And trying to ensure after the deployment of a drug that it is in fact safe when exposed to the entire population is ongoing. So if you want to discover a cure for cancer or a drug to treat mental illness with fewer side effects, you're looking at a 20-year process, maybe more, to try and come up with a new solution. Quantum computers have two potential algorithms that people might want to use for drug discovery. And I'm not going to get into what these things are, but just so that you know their names, there's the variational quantum eigensolver, or VQE, and there's quantum phase estimation. Both of those algorithms are helpful at this stage of the process. When you're at the drug discovery portion, you have 5,000 to 20,000 possible molecular compounds that you're hoping will help treat particular mental illness, perhaps. And figuring out which of those 20,000 drugs is promising enough that you can predict, at least in principle, what it should do to treat the illness is very difficult. And it accounts for a very large chunk of the overall drug development timeline. So quantum computers, these two algorithms that I've just shown, the VQE and the quantum phase estimation, those are both hoped in different contexts to be useful at looking at those 20,000 drugs and saying, well, I can predict what, most of these do is not going to be what we want. So here's a refined list of much more promising candidates within that pool of maybe 200, 250 drugs that we want to move to the next phase. And if we can address that bottleneck, we could accelerate the process of the development of new medicines and potentially save a lot of lives. It's one of the applications of quantum computers that I believe is probably, in my view, is one of the most promising and exciting. But there's a final, there's another side to this, and I'll kind of leave this here. I'm a big proponent of ethical technology development, and so I want to pose an ethical dilemma. The same technology that you could use to discover a drug to treat an illness might be used to discover a compound, a toxin, perhaps, that could be used to harm people. Same technology, just in different hands. And maybe it's a nice discussion topic. I can stop the recording in a moment to hear what you all have to think. But how would you deal with this? It's kind of like nuclear technology. One of them can be used to make energy that is carbon neutral, that we could potentially use to help us in our transition away from fossil fuels. But nuclear technology can also be used to make weapons that harm people. So how should we handle this ethical dilemma in the context of quantum? And that's where we're going to leave this. I'm going to stop the recording here.